Thank you for having me here, and it's a pleasure to give this talk to what are by now, I suppose, experts in quantum cosmology, so congratulations to all of you. But I should start, since I already got a question on my slide, with explaining the title, which will in turn explain the spirit of this talk a little bit. And so the title of the talk is Cosmological Ising Models. And, well, the first term, cosmological, is clear. This has to do with trying to understand a particular type of physical system, which we call cosmology, which has to do with the behavior of space-time in contexts where it's experiencing expansion. This is something we observe in our universe for all the periods of its existence that we can measure. And the word Ising is inspired by the Ising model that we use in statistical physics, which is a simplified toy model for magnetic behavior near the Curie temperature, the critical temperature. And what I want to take from that is that even though a physical magnet is a rather complicated system built from atoms and electrons behaving in rather elaborate ways, one can capture the essence of some of the questions one is interested in by replacing the system with a simple system of spins subject to statistical fluctuations that can either point up or down. And one can see the nature of the phase transition from simple systems of that nature. And in physics, when dealing with complicated questions and in the necessity of theoretical models, it would be nice to have analogs of the Ising model in other contexts as well. This could apply to quantum field theories or black holes, and I'll discuss that in more detail later, but also in cosmology. And so the spirit of this talk is to see what kind of Ising models, in quotations, there are in the context of cosmology. There's a slightly more nuanced sense in which I'm using the term Ising, which has to do with the fact that near criticality, the Ising model is described by a two-dimensional conformal field theory. And we'll see that two-dimensional conformal field theories will play an important role throughout the talk. Okay? Now, I don't know what the rules are, but if you have questions, please feel free to ask me. Okay, so this work is based on many discussions and collaborations throughout the years, but the work that I'll discuss today is particularly based on work by an excellent PhD student of mine, Chiara Barraco, one of our former postdocs, Teresa Bautista, who I believe passed by Paris at some point in her career, and an excellent postdoc at the Institute for Advanced Study, Beatrix Muhlmann. Okay? So let's get to it. And I should say, the beginning of the talk will be slightly more, I'll try to articulate the motivation and context in a slightly broader sense than one typically does in a seminar. And I hope that's okay with you. I felt it might be appropriate. It's also in part for my own understanding of the problem that I did this. So let's go through the motivation and context. Our theoretical understanding of cosmology currently is based on the successful implementation of effective field theory, low-energy effective field theory, coupled to classical methods in general relativity by and large. This is the methodology we use to think about cosmology at the classical and slightly quantum level. This should be contrasted with the theoretical development of questions that we've asked regarding the nature of black holes, which often supersedes the toolkit of effective field theory. It is likely that a more complete picture of cosmology will require us to go beyond the current methods. Part of the reason for this has to do with the fact that in the very early universe, there is a possibility of a Big Bang type singularity, perhaps space-like singularities that we have to confront. But also in the deep infrared regime of cosmology, we may not have complete control of the quantum behavior of the system due to large infrared effects. So there's context in which cosmology may require us to develop tools that go beyond the current toolkit of effective field theory. In order to do so, at least in other contexts, we've had some guiding principle or guiding toolkit that has helped us sharpen our questions. Examples of such guiding principles include, for instance, supersymmetry or the superstring theory, which has helped us in quantum field theory and black holes enormously throughout the years. The ADS-CFT correspondence, which has been a framework that has helped us sharpen our questions about quantum gravity in very specific contexts, not the cosmological constant so far. Ideas about the holographic principle, which are on a less sharp footing than the previous statements, but have been conceptually important guides. However, I think it's a fair statement that at this stage, our understanding of cosmology has withstood many of our canonical methods and toolkits. Okay? So this is part of the challenge at hand. And I should add to that part of the reason that cosmology has resisted these methods is that it's much, and I assume that part of this was emphasized throughout the course that Marc has been teaching, that part of the challenge with cosmology is that the kind of observables that we like to compute in other theories of gravity, for instance, the scattering amplitude in Minkowskian space, are not available in the context of cosmology. We don't have a nice set of sharp diffeomorphism invariant observables that we can work with at the same level that we do in asymptotically Minkowski space or anti-de Sitter space, for instance. Okay, so this is part of the challenge. Now, part of this introduction, it might be instructive for the audience to elaborate slightly with an imperfect view of how to contrast the problem of cosmology with other problems that we study in theoretical physics. Yeah? And I emphasize here the theoretical part. So let's start with black holes. I'm going to give you a very brief history of, a biased and brief history of black holes. This is not meant to be complete, but it is meant to give you an indication of the developments, starting well over 100 years ago with the Schwarzschild solution, the first exact solution that wasn't pure Minkowski in the Einstein system of partial differential equations, proceeding quite soon to results regarding the collapse of stars into dynamical processes in relativity, to discussions about theorems, the mathematical period of GR, where theorems were proved about the generic collapse of spacetime into a black hole horizon, the discovery of the Kerr solution, which remains one of the most remarkable solutions known to these equations, if not the most remarkable. Entering a period where quantum effects start to play a role in the 70s with the Hawking radiation, the notions of thermodynamics of black holes, the idea that the black hole horizon, far from being featureless, harbors an enormous microphysical entropy, speculation at the time, notions of Euclidean gravity, gravity Euclidean signature, the development of supergravity, all these major theoretical ideas, I should say, in a period where astronomers were not convinced that black holes are physical entities in the universe. In the 80s, further developments between supersymmetry and black hole were developed. The first supersymmetric solutions of black holes were found in supergravity. And concepts about placing black holes in boxes, which eventually guided us to ways to define the theory of black holes in a more stable sense, were developed. And notions of quantum information and precision calculations of black holes start to appear in the 90s using deep brains, methods in string theory and supersymmetry, and the onset of ADS-CFT, and the introduction of notions of quantum information and entanglement into the story of black holes. Okay? And finally, in the more recent period, there has been an interesting interconnectivity between black holes and condensed matter systems, quantum information, and an emphasis on lower dimensional methods. Okay? So the point of this slide is to show you that the toolkit that we use in the context of black holes is vast, is by no means a toolkit constrained to effective field theory. It's a very interesting playground that has incorporated many methods in many contexts. And the reason for this is that in the onset of questions regarding the compatibility of black holes with quantum mechanics, a certain collection of theory targets was created for black holes that required tools to study them that went beyond just the low energy effective field theory. So we had a concrete target, the quantum information content and unitarity, the Hawking paradox, and we had to develop tools to address this target. And these were theoretical tools. Yeah? Of course, although back then astronomers didn't believe black holes exist, nowadays they certainly do. It's a great result of the last 10 years. LIGO has seen mergers, and with that new methods appear, including scattering methods that try to describe the mergers of black holes. So there's a nice interplay between the necessity for theory tools for phenomenological purposes and theory tools for conceptual questions of principle. And like I said, the theoretical toolkit is vast, and the list I repeat over here. And a conceptually crucial role in the story was played by isolating the question of black holes sufficiently from many other parameters, sort of the Ising model of a black hole in the context that I'm using it, placing it in an isolated form in a box where we can measure it with great precision and try to deduce the microphysical nature of the black hole. Yeah? Okay. This helped us render the problem sharp. It rendered concrete calculables to study the problem, and this has been an important back and forth in the development of the theory. Now, even briefer than before, let me mention that a similar story can be told for the quantum field theory. So an even more condensed version of this are some of the theoretical developments that were not directly tied to phenomenology, but strongly tied to questions that we needed to understand about quantum fields, yet again date all the way back to the 1940s. And I should say that already in the 40s, Onsager finds the exact solution to the 2D Ising model in a period where it was claimed by Ising that upon failing to see that there was a phase transition in the 1D Ising model, that there was no phase transition in any higher dimensional Ising model. And as a crisis was solved in condensed matter by showing that the 2D Ising model, solving it exactly and showing that the 2D Ising model indeed had a second order phase transition, and that the critical exponents disagreed both with the mean field approximation of Landau and Ginzburg and with experiment. So this was a very important theoretical development because it meant that mean field need not be the answer to everything, but that also there can be many models that we can study in order to develop the problem. And soon after Onsager's solution, I should say, it was proposed that the 3D Ising model, which will be solved in a matter of weeks, would be the way to make contact with experiment. Part of that statement was true. But the point is that the role of the 2D Ising model was crucial in the development of ideas. In the 50s and 60s, the development of the S-matrix, Yang-Mills theory, spontaneous symmetry breaking, quarks, and also 2D solvable models, including the model of Schwinger of two-dimensional quantum electrodynamics, where Schwinger proceeds to solve an exact two-dimensional quantum field theory because he needed to understand whether or not gauge fields can acquire a mass in a gauge-invariant way, are developed. This is as back as the 50s and 60s, this perspective and this playfulness, theoretical playfulness. And the list goes on. In the 70s, we have, of course, major developments in gauge theory normalization, but we also have important developments in solvable models, the Yang-Baxter equation, Tufts solution of 2D QCD at large n, and so forth. In the 80s, we see the onset of conformal invariance, superconformal invariance, 2D CFDs, a beautiful paper of Belavin, Polyakov, and Samologikov. And in the 90s, supersymmetry starts to show clear signs that it can play an important role in these questions of Yang-Mills, D-branes, ADS-CFD. We start to see commonality with black holes and string theory. And in the recent time, many old ideas are revisited, modernized, and systematized into a very exciting program. Okay? But again, the point to make in this slide is that the toolkit one develops for quantum field theory is vast and playful, and again, tied to a very crucial theory target. Here, the theory target is what is the nature of strongly interacting many-body quantum systems? What is the nature of strongly coupled quantum field theory? And how can we tackle such questions, respective or irrespective of phenomenological constraints, eventually looping back to phenomenological questions of interest? Okay? So, interestingly, and again, the tools, which have an interesting overlap with the tools for black holes, involved symmetries, supersymmetry, lower dimensional models, Euclidean methods, for instance, with instantons, perturbation theory, mathematics, and large computers, and have an interesting overlap with the tools that we've used for the black hole problem as well. Both motivated by separate theory targets, and both developing a rather theoretical playground. Okay, so this is something that one can reflect upon when thinking about where the theory of cosmology at the quantum level stands. Yeah, so this was my somewhat general perspective of what to compare the current state of theoretical cosmology to if we are interested in doing that. And so it seems that we may have two types of questions that we need to address in cosmology. A, what kind of theory targets are there meant to be? What is the analog of the Hawking paradox or the strong coupling problem of quantum field theory in the context of cosmology at the quantum level? And what kind of tools are we willing to develop in order to address such theory targets? And it is my view currently that both of those issues are underdeveloped in the context of cosmology, which is not to say that we don't have strong and important questions that we ask. But the sharpness from a theoretical point of view and the type of theoretical toy models that we have to ask them seem to be on a slightly different footing than the analog of quantum field theory and black holes. Okay? That can be debated, but I think this is the perspective I'll take. Now, we could, ask whether it's because ideas in cosmology developed later than those in quantum field theory or black holes, but that's not true. In fact, 1 year after the discovery of the Schwarzschild solution, de Sitter wrote down his metric of the de Sitter universe. FLRW solutions did not come much later than that. And so cosmology has been part of the conceptual understanding of theoretical physicists for a long, long time. And observationally, it far precedes the observation or the general established observation of black holes. This was already in the era of Hubble, followed then by the observation of the cosmic microwave background radiation, evidence for Big Bang nucleosynthesis. Early articulations, which is one version of a sharp problem, of the cosmological constant problem by Zeldovich, already in 1967. The idea of Wheeler and DeWitt, cosmological singularity theorems of Hawking, already in the 60s and 70s. And so the development of cosmology has had just as long and rich of a history as the other topics. But if you ask me what is the analog of a BPS black hole in 11-dimensional supergravity for cosmology, or what the index theorem is, I will have a harder time answering that question. Yeah. Of course, it may indicate that it's a harder problem, or it may indicate that we haven't framed the question in that way. Okay, and this list continues. Yeah? So, one of the questions then that we may wish to ask, much like we did for string theory, much like we did for quantum field theory, and much like we did for black holes, is what do we really mean when we say cosmology? What is the theory of cosmology? Do we have a framework for cosmology? And I think to date, we do not even have the rough shape of what a complete theoretical framework or toolkit would look like for quantum cosmology. And this is to be contrasted with the modern idea of a black hole as a microphysical system of strongly interacting, rather chaotic degrees of freedom that create very specific signatures in their two-point function and four-point function and so on. Notions of monopole condensation, confinement, Yang-Mills, putting Yang-Mills on the lattice. It's to be compared with that standard that I'm making this point. Yeah? We do not have a mathematical theory or the rough shape of mathematical theory of cosmology. And the question is whether we should be at this stage as theoretical physicists, being aware of the cosmological nature of the universe, trying to sharp this kind of a question, or maybe this question is too ambitious. Okay? So this is, this was prompted, I should say, by PhD students of mine coming to my office and asking me, what is cosmology? Because we are in a mathematics department, you see, at King's, and what is it? What are the rules? What is the... Because they were seeing talks about the conformal bootstrap, about the S-matrix theory, about supersymmetric microstate counting of black holes. And they're like, okay, so what is it? And I failed time upon time to answer those kind of questions. But I did like the spirit of the question a lot. Yeah. Now, the question has been asked before, so I can't claim any credit for the question. In fact, it was asked by Bondi, and so I can give you an opportunity to read this monograph from a book of Bondi I found on cosmology in the King's Library that was written in 1952, which I consider to be a rather modern perspective of theoretical cosmology, where he goes on to say that we should construct mentally a number of different models of a universe and investigate their physical properties. He says that it's not surprising that such a mode of attack led to a considerable number of model universes, each of them interesting and remarkable in their own right. And, well, this is a strong statement. The question of which one of them was the actual universe became of lesser interest. Okay, I'm not sure I agree with it, part of Bondi's statement. But the spirit of this paragraph, which is the opening paragraph of his book on cosmology, which is before Penzias and Wilson observed the CMB, I find remarkable. He's imagining many possible consistent models obeying rules of cosmology. He talks about the axioms of cosmology, and what are these things? Yeah? So this was certainly a question in people's mind, and so it's in fact an old question. But I very much like this paragraph. It took me by surprise. Yeah. Which one of these possible universes is the actually real one becomes a secondary question. These are very strong words. Again, this is Bondi's words, not mine, but I want to show you what in the early days of cosmology and the theory, people were trying to confront the kind of questions they were. Yeah? And Bondi, for those of you who are unfamiliar, played an instrumental role in the development of the theory of gravitational waves, interestingly, and the notion of symmetries in Minkowski space. It's curious that someone like that was asking questions like this. Yeah? I think it's humbling for a lot of us to reflect on this, but anyways. All right. Now, in recent times, just to bring the conversation back, so now we're going to start collapsing the wave function onto less open-ended questions, but I needed to go through this, and so I felt it was useful to go through this with you. But in recent times, there has been a little bit more of a concerted effort to identify theory targets in cosmology. I wouldn't say we've reached the final point of this, but it is nice to see in the literature that the theory targets that cosmologists are discussing seem to lie in two different veins. One vein is a little bit inspired by the way we think about black holes, where people are trying to understand Euclidean notions of quantum gravity in the same sense that Gibbons and Hawking were thinking about black holes in the 70s from the point of view of cosmology. There is further work on a very special solution to the Wheeler-DeWitt equation known as the Hartle-Hawking equation. People are trying to understand its nature. There's more quasi-local ideas surging. The role of the observer in cosmology is starting to play a role in theory discussions, and rather mathematical theory discussions, which is a novel perspective, and so forth. And there's also a QFT branch of work that has started to grow recently, which tries to systematize our understanding of quantum field theory in curved expanding spaces using modern methods that are derived, either new methods or derived from conformal field theory that try to use symmetries in stronger ways than previously. There's a lot of work on tree-level methods, but also quantum loops are starting to appear in the discussion. And a lot of it uses more heavily the isometries of certain very isometric spacetimes. The question of unitarity and its role from a group theoretic point of view is starting to appear in the literature. And so I can report at least that recent years have seen a slightly more concerted effort in trying to develop sharper theory targets. For instance, we could ask the question, does there exist a quantum field theory in a de Sitter background that's fixed that we can solve in the same way that we solve an integrable quantum field theory in Minkowski space? This is a kind of question that people are asking, and these questions are yielding answers. just to give you a flavor. Or people are starting to ask, how far can we go in the Euclidean calculations if we try to compute loops, quantum loops? This was a problem that had not been addressed in 50 years, and recently people are starting to compute quantum loops. Yeah? And in doing so, interesting ideas and surprising results surge. Okay? I can't review, unfortunately, all of these recent developments for you. But now, in light of the class that was being taught, I'll focus on one very particular avenue that has played a role recently. And so of these novel methods, and some of them less standard, two appear to be at least curious or underexplored. One, as I said, is adding time-like features or boundaries or the notion of an observer as an auxiliary device. This is an understudied piece of methodology that we may wish to take seriously. And I should say, after all, the way we deduce the nature of the large-scale structure of the universe, in fact, comes from making measurements in a rather local region of space-time. And if physics has to do with the way we make observations, we may wish to take this idea seriously. It's a fun exercise. I don't know if there's any students in this room, but it's a fun exercise to calculate the ratio of the size of the largest satellite on Earth to the size of the visible universe. It's a dimensionless number. And compare that to the size of the TV scale divided by the size of the LHC. The numbers, anyway, do the exercise. Okay. And another set of methodologies a little bit inspired by the Ising model, the Schwinger model, these many of the lower dimensional methods in gravity that have played a huge role in its development, has been what happens if we start to remove certain degrees of freedom or space-time dimensionality in the problem. Is it a situation where we throw out the baby with the bathwater, or is it a situation where we can still keep some of the interesting theoretical questions at hand while simplifying the problem sufficiently that we can hope for exact solutions? Yeah? And perhaps surprisingly, the amount of work done on these kind of questions, and I'll focus in light of time on the latter, compared to analog work in quantum field theory and black holes, is quite minute. There is no canonical literature on lower dimensional models of quantum cosmology, and so we cannot assess, I think, given the current status, whether or not this is a good avenue. The avenue has to be explored first. Yeah? So much like it was for quantum field theory, and it yielded time after time after time, and much like we did for black holes and quantum gravity. Okay? So, like I said, I don't have enough time to discuss all these possible avenues, but in light of the context of this talk, I will try to report a little bit on the latter. And in doing so, I'll already raise my exclamations and say that please note that when going down in dimensionalities, we must exercise significant care, okay? This is a rule. I know this rule well. I resisted for a long time in my own career going down in dimensions. Sometimes I did it, then I retreated. It's a delicate thing. However, it's a thing that we have to take into account in our theoretical toolkit. And so let me quantify what I mean by this. And so, given what we are trying to retain in the type of quantum toy model or cosmological Ising model, here would be a list, maybe too ambitious, of things we may wish our model to retain. Yeah? So here's my rule book. And then we see if we fail or succeed in identifying a model. So the rule is, I would like the theory to admit a semi-classical limit with a small but non-vanishing quantum gravity fluctuations. In other words, I want the analog of a limit where the fluctuations of the metric can be systematically computed and book-kept, not a model where they're uncontrollably large or non-existent altogether. Okay? So this is one of my rules, because this is the regime where I can compare two ideas in 4 dimensions. Rule number 1. Rule number 2, I would like my model to have locally propagating quantum degrees of freedom. I need, since I would like to be able to make at least approximately local measurements in this theory, I don't want it to be completely topological. I would like there to be fields that I could in principle use to measure notions inside of this space-time. So I would require the model to have locally propagating degrees of freedom. Okay, this separates it from something like a topological field theory. I would like the...
But would that exclude also these mini superspace models where things depend only on time?
Mini superspace is, I'm excluding on the following basis, that this is, at least to my knowledge, not a controlled approximation. It is a truncation where we have to be careful, and I don't know how to quantify how poor or good the results that it yields are. What I would like here is different. So I'm trading mini superspace with lower dimensions, but I retain all the degrees of freedom of the model. So I will make no mini superspace approximation here. This will be the perspective. So in higher dimensions, we cannot control all of the degrees of freedom, so we truncate. Here, we reduce in dimensionality. Yeah. So my hope will be that even though, and it may be too ambitious, that even though I want to keep all of this, I will not employ the mini superspace. Or, well, I'll qualify this statement momentarily. From the Euclidean perspective, this is a slightly technical statement, but let me summarize this by saying that certain Euclidean path, and if the model admits a definition in both Lorentzian and Euclidean signature, I would like the Euclidean signature theory to have a well-defined path integral. In other words, one that does not display infrared divergences or ultraviolet divergences, and I will give a model that fails this condition. In the semi-classical limit, I would like the model to have classical solutions that display the analog of Big Bang and Big Crunch cosmological singularities. I would like the Wheeler-DeWitt equation to display multiple solutions, as we believe the Wheeler-DeWitt equation in 4 dimensions does. So this should be a model that at least semi-classically has multiple solutions, not a unique dimensional Hilbert space. And finally, I would like it to the model to be loyal to some of the unusual features that we see in 4 dimensions, like the analog of the Euclidean conformal mode being unbounded. So this is a rather stringent list, yeah, and it's my price for going to 2 dimensions. And I should say, and it may be true, that perhaps this list is too stringent. It excludes, for instance, the de Sitter JT, Jakiv-Teitelbaum gravity, as a viable model, because that one has an infinite sphere path integral, no local degrees of freedom, and so on. It would exclude a pure theory of 3-dimensional gravity, but not one that has scalar matter fields, for instance, and so on and so forth. And however, it seems like a reasonable starting point if we can approximate it in any way. And so what I've been trying to do in a recent paper was identify a model that seems to have some of these features, which was a model that was discussed many times in the past in different contexts, not specifically this context, but I will borrow from the past and add to it, okay? And it's building on old work from many different physicists. And the essence of the model will be a model that is dictated by, it has a component which is a quantum fluctuating 2-dimensional metric spacetime. The action is given by the following term over here, which in 2 dimensions you may recognize as the Gauss-Bonnet term. It's a topological invariant with a coupling that allows us to control the effect of topology. However, I'm adding to this model a cosmological term of the same type that we have or appear to observe in our own world. And I will enforce that lambda is positive, and we will see why this is an important requirement for the model, and also appealing due to our own world. And I will add to this a conformal field theory built out of local propagating degrees of freedom. So this is a conformal field theory that resides in this dynamical background, yes? And these will constitute my matter fields. And the CFT is characterized by a central charge C. I will denote by C. And we will consider, in fact, the limit where C is quite large. For instance, 500 million. Yeah, so large, really, really large. Not infinite, but large. Okay, and the theory can be defined in both Euclidean and Lorentzian signatures, so we can access with it in principle various questions. Okay, so this is the beginnings of our model. And the question is, can we solve this model? Exactly. Yeah, this is the rules, and this is. So we can already see, at least it has, I haven't established the first bullet point. I've established the second. I haven't established, well, any of the other ones, in fact. So we will try to start establishing whether or not it satisfies the other bullets. Okay? Okay, but here we have it. So please try to record in your mind the nature of this theory. It's a very simple theory, but it is a theory that reminisces, if you squint your eyes, replace this with the standard model fields and this with the Lagrangian universe, a type of 2D model of our own world. Yeah? Okay, so let me now begin with an analysis of the model by taking a phase space analysis, and let me explain what I mean by that. So I will consider the following analysis of the model. I will take the sector of the CFT to be in a particular state or configuration, and the analysis I do will be such that the CFT is in an energy eigenstate. One can consider it to be in a more general state, but in the analysis that follows, I will consider my CFT fields to be in a particular energy eigenstate. And when the CFT is close to its vacuum state, and the theory lives on a compact Cauchy surface, I should say, I will consider both compact and non-compact Cauchy surfaces, which in 2 dimensions is either the line or the circle. I would have also considered intervals or half intervals, but we will not do that. But we will mostly consider the Cauchy surface to be a circle, which is the analog of a compact Cauchy surface in higher dimensions. And and the essence of the semi-classical limit comes from the following simple observation, that you may know, and if you don't, take my word for it for the time being, that a conformal field theory on a compact spatial slice has a Casimir energy. It has a negative energy, and the size of this energy is proportional to its central charge. It's something like, for a circle of size 2 pi, it's minus c over 24 pi or so. This is a formula that 2D CFT people know well, but it's important. It has a negative energy. On the other hand, in the presence of dynamical gravity with a cosmological constant, the universe is supplanted with a positive energy coming from lambda itself. So schematically, we may hope that this theory, even though gravity on its own does not support non-trivial classical solutions, in combination with the effect from the conformal field theory and Casimir energy, there may be a balancing act between the positive energy from lambda, the negative Casimir energy, such that you can harbor non-trivial classical configurations of the geometry. Okay? So that's the spirit of why we picked lambda to be positive. And the semi-classical limit will be that if we want the solutions that it produces to be large, parametrically large, we will have to take the parameter, the central charge, to be very large. That's what controls the size of the universe. Okay? So that's the intuitive physical picture, but one can render that quantitative. And I should say that this way of producing a large microscopic cosmology with effects that come from a quantum origin, because the Casimir energy comes from a quantum origin, in fact, often mimics attempts to construct cosmological solutions in string theory. We need to often balance quantum effects with more classical effects. Okay? So the energy of the conformal field theory will be denoted by E, and this is the energy of the conformal field theory as measured by a conformal clock. Yeah? So the metric, one can always go to a frame where the metric, the physical metric, is equal to something as follows locally, because we have 2 diffeomorphisms, so we can always go to a frame of the following. And I will switch back and forth between the notation e to the 2 phi and omega squared. And the energy is equal to the Casimir energy, minus 24 pi, plus the energy on top of this that the CFD fields have, okay? This is the Hamiltonian of the combined theory, I should say. It's the constraint associated with the invariance under time translation. So you can, I guess, following your lectures, decompose your 2D metric in terms of a lapse, a shift, and an induced metric along the spatial slice, omega squared. Yeah? So these are your ADM variables. And you can now identify the constraints associated with the fact that n and nx are essentially Lagrange multipliers that impose constraints. The Hamiltonian constraint takes the following form. Yeah? You have the energy from the matter sector and the energy, quote unquote, from the gravity sector. And the energy from the gravity sector has a term that is related to the cosmological constant. I don't know if you did the Wheeler-DeWitt equation for including a cosmological term. Yes, so this one you could identify. And there's a term that's quadratic in the conjugate momenta of the fields that has what you would call the wrong sign kinetic term, which is this thing of the Wheeler-DeWitt equation that it has a Klein-Gordon type nature. So that is preserved in the nature of this Hamiltonian constraint. And then there's a momentum constraint that has to do with invariance under tangential diffeomorphism that points along the Cauchy surface as well. So these are the constraints of the theory. And the momentum constraint is linear in the conjugate momenta. The Hamiltonian constraint is quadratic in the canonical momenta and has the wrong sign, which allows you to harbor non-trivial solutions that have positive matter energy with the negative gravitational energy. This is how GR, although it has vanishing energy, can have many non-trivial solutions, which appear to be like positive energy solutions purely from the matter sector. Okay?
But this term comes from where in the Lagrangian? Because you have a total derivative, the Einstein-Hilbert.
It comes from this term over here, because in contributing this over here, one has derivatives of the metric as well, and they modify the canonical momenta of omega, of the induced metric, and so forth. So it's crucial for the consistency of the theory to add this term. In fact, without this term, we know well that it makes no sense to do an ADM analysis of this theory. And so, indeed, so you're absolutely right that these terms are crucial, crucially connected to the presence of the matter fields. Yeah.
But the specific form of this term will not depend on which action you choose for the matter field?
No, good. So the CFD, if I had chosen a matter theory that was not a conformal field theory, it would depend on the delicate details of the matter theory. In choosing a CFD, and assuming that the topology of my space is trivial, there is something quite remarkable about how a CFD perceives a curved space in 2 dimensions. And it perceives this essentially through what's known as the Polyakov action. And so you can control very precisely, in an almost model-independent way, how it contributes to the ADM analysis. Yeah. So that was why, in that way, I justify for you, in the spirit of solvability, why I selected a conformal field theory. You could generalize the analysis by trying to add a small relevant deformation to the CFD and try to do small deformations around the conformal analysis, and that would be an interesting thing to do, to go slightly away from the current analysis. But for the time being, I wanted the most solvable of all cases. Yeah. Okay. In addition to the constraints, we also have the Hamilton evolution equations that can be computed. Yes. And with that, we have at our hands this phase space. And by classical, again, what I mean is that I'm scaling C and lambda. Lambda I can always relabel by C times lambda tilde, yeah? And I'm imagining a large central charge, which, as we will see, harbors parametrically large solutions, yeah? Of course, I should be cautious in my terminology classical when it comes to the CFD. So those fields I'm treating their quantum contribution, but I'm doing it in a self-consistent way. Okay, so now that we wrote our equations, we can ask what are their solutions. Yes? So because of this decoupling of the conformal mode to the CFD, I can effectively solve the 2 problems almost independently. So I can study the problem in the CFD in these different energy eigenstates. One in principle could do more elaborate states, but I'm sticking to energy eigenstates. And what's left is an equation that the induced metric along the spatial slice is obeying. And I have at my disposal one function worth of ambiguities of the tangential diffeomorphisms that I can use to select a gauge where omega, at least in the local patch, is independent of the spatial coordinate, because I have one function which I have not used up, which is my spatial diffeomorphism, and I have one function that is subject to its transformations. But all of the matter fields, of course, I cannot set to constant values. That would be doing the mini superspace. So here I'm imagining that the matter fields are in whatever their wave functional is, complicated wave functional, and I'm using my diffeomorphism to iron out any wrinkles in the induced spatial metric. Okay? Good. Now, the solution space of these semiclassical equations splits into two behaviors. One behavior happens when the energy of the CFT is below C over 24, which is our Casimir energy. And the nature of the classical solution there exhibits what one might call a classical bouncing cosmology. You have a world that starts large, goes to a particular minimal spatial size, and then becomes large again. The de Sitter solution is of this type, and in fact is the solution to the theory wherein the energy of the CFT is sourced purely by the Casimir energy. When the CFT energy, after going through a degenerate point, becomes larger than C over 24, which is the CFT in a very, very highly excited state, this throat becomes a point and eventually splits off, and one has two solutions which start off or end with a Milne-type singularity, where the universe closes up to a point, yeah, and either expands forever or forever contracts. Okay? Now, ordinarily, when the universe starts to shrink to a small, small point, the regime of validity of my theory would disappear. However, the model we're studying is a renormalizable theory in the quantum field theory sense, and we've integrated out the CFT fields exactly. So it is not subject to things like higher derivative terms. And so in principle, if I view this theory by the standard rules of quantum field theory, I can trust this theory to arbitrarily small circles. I can keep track of the dynamical evolution all the way to the Big Bang. Yeah? So we may be able to ask questions. And moreover, since I have access to the matter fields and the precise state that they're in, I can describe what kind of state the universe is in at that point. It's a complicated, highly excited state of the conformal fields with a very particular regime of energies. Okay? So that's the picture. And the equation that goes by the picture is that the metric for this kind of universe, or the time reversal of it, because when you have one, you have the other, it takes the following form. Okay? There's a 1 over sinh t times the square root of 24 pi e over c minus 1. And I want to point to two things here. T goes from minus infinity to 0. So it's a cosmological clock that goes from minus infinity to 0. At minus infinity, the universe shrinks to a point. At t going to 0, you can approximate the sinh with its argument. And the energy dependence between the numerator and the denominator cancel. So the late time limit of this metric no longer senses the energy eigenstate. This is what people call in cosmology something like the no-hair theorem. Some of the features of the initial state are washed out by the large-scale expansion. Okay? And the other thing I want to make is that varying the energy of the CFT fields, we expect to be a physical thing. And so it should have a physical effect on the geometry, and it does. It varies the length of the minimal spatial cycle of the universe, which although locally you can do a diffeomorphism to change, globally you cannot. So indeed, varying the energy of the matter fields varies the size of the universe, and in a way that looks just like gravitational back reaction. The larger the gravitational energy, the more it shrinks the universe. Yeah? So it has that flavor as well. Okay. And like I said before, all solutions are indistinguishable at sufficiently late times for any observer that samples only a finite, potentially large region of space. Okay? So this is what so going back to our list, it appears that this classical phase space of this theory harbors interesting cosmological solutions, and we can moreover keep track of the nature of the solution all the way near the Big Bang, which is reminiscent of attempts people had in 2 dimensions to keep track of the Hawking radiation of the black hole all the way to the final point, or the remnant. Okay? Now, what one would like to do at this stage is quantize this theory exactly. Not approximately, but exactly. We do not have the tools to do this, but there is a very compelling conjecture on how to do this in 2 dimensions, which comes from a lot of work in the past that related 2-dimensional quantum gravity coupled to a minimum model to Liouville quantum field theory and matrix models on the other side. Yeah? And what that work, part of what that work accomplished, it accomplished many things, was that they gave a very good proposition for what the measure, the path integration measure, or the quantization of the 2-dimensional metric is at finite coupling. In other words, not just at large C in our context, but at finite C. So we're going to use this conjecture to quantize the model in the way that people quantize 2-dimensional quantum gravity and compared precision comparison to matrix models in the past. So this is what I'm calling the Liouville quantization. And the Liouville quantization has one slight drawback, which is that you have to work in a particular gauge. So this was the conformal gauge. So we have to go to the conformal gauge here. And I'm going to analyze this conjecture in this gauge and see whether in the large C limit, in the semi-classical limit, the results of the quantization match this classical analysis that we saw over here. So we have something to compare to that came from an independent method of analysis. So what does it mean, Liouville quantization? Upon implementing the conformal gauge, we can view the theory, so this is the essential proposition, the quantum theory, the complete quantum field theory, as a combination of a Liouville quantum field theory, which I'll specify in a moment, a BC ghost theory that comes from the fact that we've gone to a specific gauge. We have the RST ghosts that we need to keep track of as well. And, of course, the matter theory itself. Okay? So this is our theory upon fixing the conformal gauge. Each of these are a conformal field theory in and of their own right. We will combine the 3 theories into a unified conformal field theory, but we must remember that we are still subject to constraints, because upon fixing the conformal gauge, there are residual constraints, residual gauge transformations that we must constrain, that the theory will be subject to. So it's not an ordinary conformal field theory. It's a conformal field theory subject to constraints rendering all states conformally invariant and all operators conformally invariant if they're gauge invariant. Okay? So this is the rule of our game. This will be our proposed quantization of the theory. And to give you some flavor for the theory, the Liouville sector, which decouples when the matter theory is a CFT, although it remembers the matter CFT in the implementation of the constraints, takes the following form. So this is a Lorentzian signature, and phi, I remind you, is another parametrization of the conformal factor of the 2D metric. Takes the following form, where Q is a parameter that people often write as 1 over B minus B, B being a real number. Phi is this field over here. Lambda is our cosmological term, which in the Liouville theory becomes the coefficient of the exponential coupling in phi. And the other curious feature of this theory, which differs from the Liouville theories that people studied often in the past, is that in this context, the kinetic term of the conformal mode phi has the wrong sign, which is precisely what the doctor ordered for the Wheeler-DeWitt equation. And so this sign, far from being a hassle, like it was often in the past, in this case is merely a reflection of the fact that this is a model for the Wheeler-DeWitt equation. Yeah? And we should remember that here we are not claiming to study the theory in and of its own right, but rather as part of this combined system that is still subject to constraints. So much like the wrong sign kinetic term of the Wheeler-DeWitt, upon implementing constraint is tamed and it's not allowed to go wherever it wants, here similarly you could imagine such a situation. Now, you may have wondered whether I've introduced new parameters that weren't fixed already by the theory, but that's not true. Q is fixed in terms of B in order for this Lagrangian to describe a conformal quantum field theory, which we require because conformal transformations are part of the residual gauge transformations of the conformal gauge and therefore redundancies that it cannot depend on. There cannot be a conformal anomaly in this theory. And since there cannot be a conformal anomaly, the sum of the central charge of the BC ghost theory, of the matter theory, and the Liouville theory have to be zero. The Weil anomaly has to cancel, reminiscent of worldsheet string theory, but different because of this time-like mode and the way we're treating it in terms of a Wheeler-DeWitt equation. And hence, Q is fixed in terms of the central charge in a nonlinear way. Okay? So this is an exact equation. So this is, therefore, linking the old problem of time-like Liouville theory with the question of whether or not we can construct a quantum theory of cosmology with positive cosmological constant. It's an interesting context for the problem of time-like Liouville theory, and I think it gives interesting motivation to solve this model. And I should say that there's a lot of interesting work, including work in France, on time-like Liouville theory from the point of view of probability theory, and people trying to solve it. In that context, they call it the non-compact imaginary Liouville theory, but actually I believe it's the same model, and I believe papers in that literature may be portable to this literature, and they may be actually solving the Hartle-Hawking path integral in those papers. Okay, just an aside, because this is a natural problem in stat mix. So, but we also see how the toolkit of 2D CFT might help us in this context, a new toolkit for cosmology. So what is the Hilbert space? Like I said, we have to solve still for the constraint equations that the Liouville mode is subject to. These become equations that the Liouville has to obey. I haven't written them explicitly, but effectively one has to compute the stress-energy tensor of the Liouville field, decompose it in terms of Virasoro modes, and impose that states are annihilated by the action of Virasoro modes, along with, well, it's the Virasoro generators, the full combined system, not just the Liouville system. But you have basically a Hilbert space that's given by the tensor product of the Liouville. Hilbert space is CFT, Hilbert space, and the ghost Hilbert space. This is a pre-Hilbert space, subject to the following constraints. And again, if I go to use my spatial diffeomorphisms to go to a gauge where the induced metric on the Cauchy surface is independent of the spatial point, I can effectively render my Liouville wave functionals as functions of the only diffeomorphism invariant geometric quantity, namely the proper length of the universe, which is what the mini superspace people would call the scale factor, the constant scale factor, the size of the three-sphere, for instance. Except here, we've gone to that by implementing a consistent diffeomorphism. And this L is, you can view as the proper length of our Cauchy surface. Yeah? And so now the question is whether these effectively differential equations that psi of L has to obey, so I can represent H and P in terms of differential equations, whether I can solve them exactly. Fortunately, well, let me give you a flavor of what they look like. So they're fairly simple differential equations. They take, so in terms of L, they take roughly the following form. They take the form of a Bessel-type differential equation. So it's a very concrete, let me check. I'm a little bothered by the sign that I just wrote down. Let me just check that I got the right sign, since that sign is the time-like sign, so I want to get it right as a matter of principle. Ah, yeah, indeed. My instinct was correct. My forgiveness. I beg my forgiveness. Yeah. Indeed. In quantizing this theory, we're selecting a specific choice of operator ordering, and the selection has to do with this being a solvable Liouville CFT. You're right. So in declaring that this is the Liouville quantization, we are selecting a very judicious choice of operator ordering, and the justification, if you want, for it is that this is the one that is consistent with it being a conformal quantum field theory. Indeed. So we have a principle that may guide us into how to disambiguate the operator ordering problem in this context. Thank you for the question. Good. Okay. So here we have the nature of the differential equation left to solve. Of course, the matter field, if it's a complicated CFT, will have a very complicated wave function built out of all the matter fields. There may be 500 million of them, and all of the details of that, in principle, we can use to study different states and configurations. But here I want to display the simplest type of solutions to the Wheeler-DeWitt equation, which we can solve in its exact form in this context. Okay? Okay, so let me proceed now to give you some, So now we'll offer you some plots. And what I'm plotting in these plots is this Bessel function. So these are exactly known functions that we can analyze in all sorts of regimes, the semi-classical regime, the quantum regime, and whatnot. And so here we have the part of the wave function that is a function of the size of the universe. So this is not the full wave function, which would include the matter and BC ghost. In fact, the BC ghost we have to set to the BC ghost ground state unless there's a non-trivial BRST cohomology that includes excited BC ghost states, but I suspect that's not the case. And so here I'm only displaying the piece of the wave function that has to do with the size of the world. And for low enough energies, which we characterize by the conformal weight of the primary in the CFT, we have two behaviors. We have one behavior where the wave function tends to 0 as the universe goes to 0 size. This is not an approximate equation. This is an exact solution. And as the universe becomes larger than c times lambda, the wave function starts to display WKB type oscillatory behavior. And the way to interpret this is, I believe, the way Hartle and Hawking envisioned their wave function, where they conjectured the existence of a wave function to Wheeler-DeWitt because they couldn't justify the part of the equation where the universe became very, very small because other terms in the effective field theory will start to kick in. Here, we can control that. And so we have the kind of wave function that they were envisioning, okay? So when the matter fields are close to their ground state. In addition to this, we have our matter state where the fluctuations can be in some sort of Gaussian state or whatnot. In addition to that, there's a wave function where at very small length, the wave function diverges as the size of the universe becomes small. And this is reminiscent of a kind of wave function that was envisioned by Vilenkin, where he wanted to be a large probability of the universe appearing at a very small size. This was called the tunneling out of nothing universe. Here, the comment I can make is that this wave function just diverges. It never gets tamed or regulated to some finite quantity. It keeps on going up and up and up, which is a somewhat curious behavior. Okay? But at large L, again, you have WKB type behavior. And what this WKB type behavior is that it matches the fact that when, for low energies, we had these bouncing universes, and so for a sufficiently large size of the universe and larger, there's a classical configuration that the quantum state can match onto, and therefore the WKB behavior kicks in only after a certain size of the universe. But below that size, there is no classical solution, and therefore you have tunneling or exponential type behavior. And so we are loyal then to the WKB analysis, and in fact we can match onto it in the large C limit. Okay? What about when the CFT fields exceed this C-1/24? Well, let's make a physical guess. In that case, and see why, and discover that we will be wrong, but for an interesting reason. But let's make the physical guess, which is we saw that in that region, we had universes of big Rang or big crunch type where this classical world could harbor a size that could become parametrically small. And so there we may expect that the WKB, or oscillatory behavior, would persist everywhere. Yes? This is the semi-classical or WKB instinct. And indeed, that is the case, modulo one caveat, which is that in the classical analysis, I could perfectly well prepare a world that once expanding was forever expanding. This would mean that I could prepare a wave function that once left moving is forever left moving, because the expansion of the world has to do with the directionality of the wave function. However, the nature of these Bessel function solutions is such that even though you can prepare the world in such a way that you have a solution that's purely left moving for small circles, at sufficiently large circles, it becomes a superposition of a left-moving and right-moving wave, except that the right-moving wave appears with a coefficient that is suppressed by the central charge. It's a tiny, tiny effect. But what it is telling you that there are small errors to the classical analysis, that even though you thought you were in a forever expanding phase or forever contracting phase in the beginning of your world, there will always be at the quantum level access to a tiny component of the wave function that is either contracting or expanding. Okay? This is something like a quantum bounce, and it caught us, I have to admit, a little bit by surprise, because I expected to see a perfect match, but there is this exponential suppression, and nothing is incompatible with it. In fact, once you say it, you can imagine it happening in many more elaborate Wheeler-DeWitt equations, and it's a new way to access bouncing type cosmologies that is purely quantum mechanical rather than classical. Yes? So this is a solution that the theory exhibits, and it comes with this suppression. Okay? That's an interesting situation. Some further remarks. We can try to construct inner products, much like much like DeWitt envisioned constructing in his early papers. And if we take the Wheeler-DeWitt type inner product, which is the one you might imagine, which is in no way the unique or perhaps even the correct inner product, but it does have the same flavor. And so the Wheeler-DeWitt inner product of the 60s applied here would yield indeed a non-definite, positive definite norm. Okay, that's a feature that it has in common. And finally, let me comment on another important paper in quantum cosmology, was the proposition of Hartle and Hawking that there exists a certain path integral, the Hartle-Hawking path integral, that produces a solution to the Wheeler-DeWitt equation that has these properties. So there's an interesting question here. We found this Hartle-Hawking wave function directly by solving the Wheeler-DeWitt equation, whereas Hartle and Hawking wanted to make the case that there was a certain Euclidean path integral that produces this wave function. But here we can test their proposition as well, because now the Hartle-Hawking path integral becomes a question of what is the disk partition function of time-like Liouville theory, which our colleagues in StatMech are apparently studying. But we studied as well. We weren't aware of that work. In fact, that work came after our work. But we can study it as well. And this path integral, I have to confess to you, I still don't know how to solve exactly. However, we can solve it in a semi-classical limit with loops. So far, it agrees with this object over here. And the other comment I can make is that if you try to compute this path integral in a two-step process where you first fix the area in the disk, calculate the fixed area path integral, then integrate over the areas, the semi-classical saddle point analysis for the function of the area that you get, that you need to integrate over all areas, is such that there exists a contour in the complexified space of areas that yields for this path integral precisely the Bessel functions we were finding. This has to do with a particular integral representation of the Bessel function known as the Schlafly representation, if you're fans of the Bessel function. And I suspect that it means that this path integral should be solvable exactly, even though we have yet to accomplish that. But my suspicion is that this path integral will indeed render for a particular contour, and this may guide us a little bit in how to navigate what choice of contour we should make for these path integrals at the exact solution of the Hartle-Hawking type in the Wheeler-DeWitt equation. Okay? And the methodology that we use to analyze it comes from a beautiful paper of Fateev, Zamenhojikov, and then Teschner, who solved this kind of path integral exactly in the space-like Liouville case using bootstrap methods. These methods have not been developed to the same degree in this context, but I believe they can be.
Again, it might be a trivial question, but again, you could choose different paths, complexified paths, so one of them would give the Hartle-Hawking, the other would give the Vilenki, right?
Or linear superpositions. Yeah. The important question is whether there exists a path that isolates specifically the Hartle-Hawking solution, you see? Or whether what they imagined it was always polluted by some other solution as well. The point I'm making is that here we might actually be able to establish that kind of statement. Okay, good. Now, as an aside, as in a question that was prompted by this analysis that we discovered we couldn't find an answer to, if you read the Wheeler-DeWitt paper, the Hartle-Hawking paper, you might actually imagine a more elaborate notion of a Hartle-Hawking wave function, where you add not only the trivial topology to the Euclidean portion, but also higher topologies as well. This type of problem is in fact an even more complicated problem, and in fact one that has, from the Liouville point of view, far less results. And here I don't have results, but there is a result in the old matrix model literature where there is an analog of this equation, but with different signs, so not quite a cosmological equation, where it was noted, not in this context, but it was noted at a technical level, that these contributions in fact no longer solve the Wheeler-DeWitt equation. They offend it, and in order to account for them, you would have to modify it. And so, interestingly, we are in a situation where we may be able to compute non-trivial topological corrections to the Hartle-Hawking equation and see what gives a modification of Wheeler-DeWitt or a modification of the Hartle-Hawking proposal of this wave function. Yeah? In higher dimensions, one may be prompted to study this kind of problem as well, because in 4 dimensions, for instance, there could be non-trivial saddles that are not the force sphere that are solutions to the Einstein equation. In fact, CP2 is an example of that, or other Kähler-Einstein manifolds in 4 dimensions. It's a very elegant geometric problem. Yeah.
But can these modifications be understood as higher curvature terms?
Good. This is an excellent question, and I don't have an answer to this question, but I have concerns. I'll leave it at that. And when we're not being recorded, I can tell you what I think. Moreover, the corrections that they found in the limit of large spatial dimension, it dominated over the trivial one. Okay. In any case, let me leave this as that. And finally, let me move on to my other bullet point. So I hope it's become clear that I've started to check, at least partially. You can be my judge and you can decide what grades to give each of my bullet points. I don't mind. Please pass me. But we've gotten at least a C- in most of our bullet points. And so finally, from the Euclidean point of view, one of my bullet points was whether or not this theory exhibits a non-trivial Euclidean partition function, which in this context, the Euclidean de Sitter is a two-sphere. And the question is whether there's a rich two-sphere path integral. And to contrast this with another type of model that people studied with is the 2D de Sitter-Jakiv-Teitelbaum model. In that model, the sphere path integral is strictly infinite, but not in a way that can be regulated with ultraviolet divergences. It's infinite in a much worse way that has to do with zero modes of the path integral that cannot be gauged away. Now, remarkably, this is the problem of the sphere path integral in time-like Liouville theory, and pieces of this path integral, again, can be calculated very exactly. And this is thanks to early and beautiful work of Kawai, Neguchi, and David. In fact, in the original literature, many of those methods are borrowed. And the structure of the sphere path integral comes from a term which is effectively topological, a term that is logarithmic in the cosmological constant, which has a prefactor which used to be called the KPZ coefficient, which here is the time-like counterpart of that. And a term that is sensitive to an arbitrary number of loops, which have been computed bias to 2 loops, and then in a beautiful paper of Beatrix, up to 3 loops, in fact. So this is really, we're talking about 3-loop calculations in quantum cosmology. This puts me in a very good mood. I hope it puts you in a good mood as well. And in fact, due to the non-trivial nature of the contour that one has to choose, there's a phase very much like the phase that was observed by Polchinski that many people are discussing in the recent literature. So it's loyal to the structures that appear in 4 dimensions, which is a further parallels that one can draw. And although this looks like a rather complicated prefactor to the logarithm, you can expand it at large C, and the first contribution it gets is a C over 6 log L squared, which may remind you of results in the entanglement entropy of a 2D CFT, something that people Cassini and Huerta studied, and Holzen, Larsen, and Wilczek studied, and Cardi and Calabrese studied. And indeed, the leading term is effectively the entanglement entropy of a 2D CFT in a rigid de Sitter spacetime, when you confine the fields to live in a single cosmological horizon. What's remarkable here is that although the C over 6 result is an exact result in CFT, here the gravitational formula receives an infinite number of corrections. And so we have a gravitational counterpart to Cardi-Calabrese, and it would be very interesting to understand the nature of these corrections from a Lorentzian perspective. Yes? So there's a flavor of the exact sphere patterning rule that may indeed allow for a Lorentzian interpretation, even though it's a rather esoteric Euclidean object. Okay. In addition, if we have access to the analog of the DOZZ formula for time-like livable, we may be able to assess whether or not complex saddles also contribute to this sphere pattern rule, allowing us to sharpen questions about the reality conditions of the theory, which may tie to unitarity. Okay? So that's my comment on the Euclidean picture. And finally, because I've overstayed my welcome, let me offer you an outlook. So the outlook is bearing, like I said, in mind, what are the lessons for 4 dimensions? And throughout the talk, I've tried to tie wherever I could to the analogies, quantitative or qualitative, of the 4-dimensional world. What the reality conditions of these partition functions, the nature of psi at small length, these quantum bounces, the nature of topology in these Einstein manifolds, and so forth and so on. Can we ask sharply, since we can track the quantum state all the way to the Big Bang, about the quantum information content of the Big Bang? After all, when we have a Big Bang, it corresponds to the case where the CFT fields are near an exceedingly large conformal weight, which is what we call the Cardi regime, where there's an explosion in the number of primaries. And so there may be an enormous number of degeneracies associated to the Big Bang in this Cardi regime that we may wish to somehow analyze and see how it would contribute at very late times to the entanglement entropy of the slice, and how it competes with the empty de Sitter entropy, for instance. Okay, so what is the late time fate of this quantum structure? Oh, and thank you for your time.